Welcome to our webinar, Military EMC. Sorry about that. Welcome to our webinar, Military EMC Changes in MIL Standard 461G. Thank you for joining us. This webinar is being hosted and presented by MET Laboratories. MET is a leader in the testing of electrical and electronic equipment for environmental hardiness, product safety, and electromagnetic compatibility. MET operates world-class labs in Baltimore, Maryland, Santa Clara and Union City, California, Austin, Texas, and also runs operations in China, Taiwan, and Korea. This webinar will run 30 to 45 minutes with an additional 15 minutes for questions and answers. Due to the number of registrants, all attendees will have their phones muted. If you have a question, please type it in the questions area of your GoToWebinar control panel. We will attempt to answer all questions at the end. Today's webinar is being presented by John Mason. John is MET's Military EMC Lab Manager. At this point, I will hand over the presentation to John.
Thank you. Welcome everybody to the webinar. The topic of the webinar today is to discuss MIL Standard 461 and specifically highlight the changes that took place between versions F and the current version, which is version G. So this is a quick outline of what I'm going to cover. First several slides are going to be an overview of the standard itself, talking through the different content, the scope of the standard, and an overview of the different test methods that are included. And then the next portion will highlight the changes in the G version of the standard. And at the end, I'll briefly cover some of MET's related capabilities. So typically there's MIL Standard 461 testing is performed for one of two reasons. Most often it's part of a government contract where some department of the U.S. military puts out a request for bid to build an electrical or electronic device, and different contractors will bid on that. And as a contract requirement, often MIL Standard 461 testing is required, and a compliant test report needs to be delivered as a part of that contract. There's often a specific form that I put a little portion of that form in a screenshot here that would form part of the contract, and that's where you would be able to find as one of the deliverable items the requirement for MIL Standard 461 testing. The second most common reason that we see requests for MIL Standard 461 testing in our lab is when a device manufacturer, either for marketing purposes or quality purposes such as ruggedization of their device, or both, decides on their own to perform 461 testing and to be able to use that as a marketing tool to demonstrate to potential clients and possibly to potential military or government agencies that their device is suitable for ruggedized applications or military applications. I'd like to note that often when the testing is done at the own initiative of the manufacturers, then if they do eventually enter into a specific government contract, they'll often need to repeat some or all of the testing, and possibly at different test levels, and maybe including different test methods that are specifically identified under that particular government contract. So I'd like to just give an overview of the scope of the standard and some of the basics of the way that MIL Standard 461 is outlined. The scope of the standard is that the standard is written to control the electromagnetic interference for systems and subsystems, but not full platforms. So it's important to note that the intent of the standard is not to test individual electronic components, but also not to test full systems. It's intended to test subsystems and equipment that will be installed on military platforms. and the standard is written by and used by the U.S. Department of Defense. The requirements in the standard are often tailored based on operational and engineering analysis. So for a specific government contract, when the manufacturer of the equipment works together with the military, they often come up with a test procedure that they deviate somewhat from the requirements, maybe in test level or frequency range or other aspects that are deemed necessary to the very specific application of that device on the specific platform that it's going to be installed and used. And like I said, the tailored requirements are documented in a test procedure. The standard uses the acronym EMITP for Electromagnetic Interference Test Procedure. And they also, I'll mention later, reference a specific document of how that test procedure should be formatted in the procedure. So the standard is divided into a main body and then an appendix. The appendix actually repeats the full content of the standard, and then it gives additional rationale and explanations for each section of the standard. And the test methods that we'll talk about throughout the standard are formatted as a 5-digit combination of letter numbers. So, for example, conducted emissions for power ports is numbered CE102. The specific numbers don't have any intuitive meanings. They're just a way to identify, but the letters in the beginning of each test method indicate whether it's a conducted or radiated test, as well as whether it's an emissions or a susceptibility test. Section 2 is just a list of applicable documents and reference documents, such as references to other standards. Section 3 contains definitions. I'm not going to go into any detail on those. Section 4 is called general requirements. So all the content in Section 4, it applies to all the tests that are going to be presented in the standard. So for example, I did highlight a couple sections out of subsections out of Section 4, which I think are maybe of a little bit more particular importance when you're actually going to try to go and conduct these test methods. So Section 431 is called measurement tolerances, and you can see there it lists whenever the standard indicates that you have to measure a distance, frequency, amplitude, so on and so forth. It gives you specific tolerances that need to be followed for those type of measurements. Another subsection, Section 4, talks about the test chamber, shielding, and the RF absorbers and a ground plane that need to be used when performing MIL-Standard 461 testing in the lab. 436 talks about the power source impedance and the requirement for the use of LISNs. LISNs are line impedance stabilization networks. And there's a couple figures that I put there. One is the basic schematic of the LISN, and the other is the graph of the impedance curve, which is, they're designed to have a 50 ohm impedance, and you can see that that is achieved from approximately 300 or 400 kilohertz on up, and it does roll down from that in the lower frequency range, just as a byproduct of the design that's needed. So when we do, when we test for CE102, there are correction factors that end up resulting that need to be applied as the result of the 50 ohm impedance not being able to be met all the way down in frequency range, all the way down to 10 kilohertz. This is just a photograph of a couple example LISNs. They usually have a metal enclosure around the circuitry. So from the outside, they kind of just appear as a plain chassis, and they have ports in the center that's the circuit that goes in series with each power conductor of the input power to the equipment under test. And in addition, in parallel to that, they have a coaxial measurement port, which is protected by a capacitor so that no DC can come through into the spectrum analyzer input. and that allows you to take the voltage measurement across the frequency range off of the individual power conductors. Another important section from Section 4 is 438. It talks about the EUT test configurations and refers to figures 1 through 5. So figure 1 shows within a chamber a table that's set up made of non-conductive material and then is covered on the top by copper. But it's a ground plane, and that ground plane has to be bonded to the earth at certain intervals by certain specific width straps, specific length to width ratio. And there's also a requirement for specific layout of the cables and how high off of the ground plane they need to be and how far apart they need to be separated. And all of this setup requirement accomplishes repeatability in the test methods. So when you perform these tests from one lab to another or one time to another, then you can expect a higher level of repeatability by standardizing the layout. So this is just a list of all the possible test methods that occur in the standard. For any given project, normally not all of the test methods will be applicable. If you glance through, you can see some of those are applicable only to power leads. Some of them are applicable only to antenna terminals. And there's other applicability explanation within each section of each test. So I'm going to go through in a little more detail Section 5 now, which Section 5 is made up of individual sections for each of these tests. And it's a complete step-by-step procedure contained for each test. It starts out with the description of the requirement and the applicability, and then it talks about which test equipment needs to be used, how to perform a verification of the test equipment, and then how to conduct the test measurements, and which data needs to be saved as a result of the tests. Also in Section 5, there's a separate table called the applicability table, and this table is used as a quick reference to determine which tests need to be applied for equipment going on specific platforms and for use in specific military branches. So whenever we do testing for the purpose of marketing or quality purposes and our clients are asking us to advise on the tests to be performed, we quote the applicable tests listed in this table. And whenever we see testing requested from a government contract, we quote the specific test requested, but we often see that the tests requested match up to this applicability table. So in this table, the A means the test is applicable. There's no further, I guess, limitation on the applicability. And the L means that it is limited applicability, and you can refer to the applicability section within each test section in Section 5, and you can get more details of what determines the applicability. And then the S means that this test is applicable if the procuring activity, meaning the military office that's purchasing the equipment, if they specify on a specific contract that one of the tests marked with an S is applicable, then it needs to be performed for that contract. So just briefly, I skipped ahead to Section 6 because it's basically the only other section to mention other than when we start going through the test in Section 5. Section 6 is called Notes, and the most important thing that it includes there is it talks about data item description documents, which they call DIDs for short, and it references 3 or 4 documents there. These are the documents. One of these is one of the documents I mentioned that can be followed when you're preparing the EMI-TP electromagnetic interference test procedure. So this document, DI EMCS 80201, is just a short document, a few pages, but it gives you the required content that needs to be included within the electromagnetic test procedure. There's another one for the test report. MetLabs always issues a test report. However, if a contract specifically requires a DID test report, which includes quite a bit of additional detail, then that's a separate service that we do offer. And MetLabs also offers to prepare electromagnetic test procedures for our clients. The other thing that's important and helpful in Section 6 is there's a link to a website where you can download MIL-STD-461G as well as older versions. And you can also download many other U.S. military standards from that website that's listed there, the quick search website. Okay, so I'm going to continue on with a little bit more detailed overview of the test methods within Section 5. I won't be going into extreme detail with every method just because that's a much longer session. We do, from time to time at MetLabs, do a 3-day long training session on MIL-STD-461, and that allows us to get into the step-by-step details of each test. But it's just not really something that's possible in a short discussion. So the first several tests that are listed in Section 5 are conducted emissions tests. So that means that we're going to use measurement equipment like a spectrum analyzer or an oscilloscope to measure the emissions that are generated from the EUT. And that means when the EUT is normally used, it's going to create as an unavoidable byproduct of its electronic operation harmonics and other electronic noise that will conduct out of its cables, even though it's not designed necessarily to conduct out of those cables. And that interference can conduct into other equipment that's connected to the same power bus or that's connected to the same data cables as the equipment under test. So there's a couple photos there. The photo on the left is showing a setup that's used when we do the CE102 calibration check. That's where we verify the test equipment before we run the test each time to make sure that all the test equipment's working properly. And then on the right side, it shows a setup for, I believe that's the, move here. Yeah, that's for the conducted emissions test measurement. So it shows the spectrum analyzer connected to the LISN measurement port. Then there's many conducted susceptibility tests in the standard. CS101 is for the audio frequency range measurement or susceptibility on the power leads. And there's several tests which inject disturbances into any antenna ports on receiver or transceiver transmitter equipment. CS109 is a structure current test where a disturbance is injected onto the chassis of the EUT. And then there's the radio frequency range in CS114. That's the radio frequency swept conducted susceptibility. And CS115 and 116 are different types of transient. So when they talk about conducted susceptibility, that means we're going to generate a disturbance in the lab using equipment to simulate disturbances which would occur on the platform where the equipment's expected to be installed. And we're going to inject those disturbances in a conducted fashion into the external cable bundles of the equipment under test. And most of these tests do that by using inductive probes which couple the energy onto the equipment under test cables. There's a few of the tests that do it using a transformer. And there's two more conductive susceptibility tests, and these are tests that are new to version G of 461. CS117 is a lightning-induced transient test, similar to, it's actually mostly taken from the method that has existed in RTCA DO160 for commercial aircraft for quite some time. And then CS118 is electrostatic discharge, which is a test also that's been done historically since EMC testing has been performed, and they use the method from IEC 61000-4-2, which is the same test method that's used for devices that are sold for like with a CE mark in Europe, as well as many other types of products. So the pictures on this page just show some example test equipment. The left side shows the rack of equipment used for CS114 testing, which contains a signal generator, spectrum analyzer, RF amplifier, and a power meter. And then the picture in the center shows the basic verification setup that's used, or I'm sorry, it's the test setup for testing and equipment under test for the CS115 and 116 tests. And on the right side is just a layout of a group of test equipment that is used for the CS117 lightning test. There's many modules that can be installed inside of the main chassis of that system one at a time in order to accomplish all the various waveforms that are required. The next group of tests that are included are radiated emissions tests. Radiated emissions tests are tests that are performed to measure the unintentional, in some cases intentional, but most of them are for the unintentional byproduct that is radiated out of electronic equipment. So it's not stuff that's intended to be radiated, other than for the RE103 test, where we do measure the antenna direct intentional transmission during that test as well. But it's mostly for the unintentional byproducts, such as harmonics and other things that are generated. And actually all the chassis slots and holes, as well as the external cables, tend to act as, even though it's unwanted and it's unintended by the design, they tend to act as antennas to transmit or radiate the emissions. And these radiated emissions tests have limits, and the amplitude of the emissions that are radiated has to be below the limits set forth in the tests. So the left diagram that I included from the standard just shows a top-down view of when we're doing RE102, which is the electric field emissions. It's a top-down view of the basic setup. So the dotted line represents the walls of the chamber, and the measurement receiver and the computer, which they call data recording device, is located outside the chamber. And a coaxial cable is fed through the chamber using a bulkhead connector to the receive antenna inside the chamber. They do show the path split there because before the test is performed, a signal generator is used to do a verification of the measurement setup to make sure all the test equipment is working properly. And then after that point, the receive antenna is connected, and it's positioned 1 meter away from the equipment under test. And the emissions from the equipment under test, which is operating during the test, are measured. And then the diagram on the right side shows some of the various antennas that are used to get through the entire frequency range of the RE102 test. And there's very specific setup requirements for those, such as the height off the ground plane and other parameters, such as the measurement point on the antenna that's used to measure the height. This next slide just shows an example of a real test setup that was performed at Met Labs, and from time to time we're able to get permission to use photographs from our real tests with our client's permission. So this is an example of a hydraulic power supply that's used on board an aircraft carrier for testing it's for performing pre-flight testing of the certain mechanisms on the V-22 Osprey, which is the aircraft that has the wings where the wings can rotate and the propellers can operate like a helicopter to lift straight off, and then they can rotate forward to start flight while it's in the air. So this system was used to, this system under test here is used to do pre-flight testing on that aircraft. And this was an interesting test and gives an example of one of the challenges that we have to overcome when doing EMC testing, because this was a diesel-powered generator. So we had to figure out a way to exhaust the diesel fumes out of the chamber and then out of the building, but we still have to maintain a shielding effectiveness of the chamber so that we don't have any ambient leaks. The next group of tests that's presented in the standard are radiated susceptibility tests. And for radiated susceptibility tests, we use test equipment in the lab to generate radiated fields that will simulate things that could be disturbing to the equipment under test. They could interfere with the equipment under test normal operation, or they could cause damage. That's something I didn't note when I was talking about the conductive susceptibility, is all the susceptibility tests do have the potential to cause physical damage to the electronic components within the equipment under test. Some of them are more likely to cause damage than others, but they all at least present the possibility of interfering with the operation of the equipment under test. So there's 3 tests listed here. The RS-101 is for magnetic fields. We generate magnetic fields and radiate those towards the equipment under test. RS-103 is for the electric fields. And then RS-105 is called transient electromagnetic field, which represents, it simulates the effect of a high-altitude electromagnetic pulse weapon detonated high in the atmosphere. It simulates the effect on the ground that would be caused by that type of weapon, and they give the test level as a 50,000 volt per meter pulse level. So we do have the ability to perform all those tests, and I do have a picture of RS-105 verification setup in one of the later slides. The 2 setups that are shown here on the left-hand drawing is the top-down diagram for RS-103. It's just showing the layout of the EUT and cables as well as the test antenna during the test, and then all the test equipment, which is a signal generator feeding through an RF amplifier on the outside of the chamber, and then it feeds into the antenna. And then the other equipment you see is it says stimulation and monitoring equipment. That would be any monitoring equipment that's for the EUT to verify if the EUT continues to work properly during the test disturbance. And then the electric field sensor is an isotropic field probe that's fed out to a display so we can control the test level field strength in volts per meter. And the picture on the right is just showing one of the more unique antennas that is used. It's a overhead bar antenna that's used to cover the low frequency range of RS-103 when we have to reach up to the 200 volts per meter levels. The next slide shows a setup of a real test that was done here at MetLabs for RS-105. For this particular test, because of the large size of the EUT, we had to perform the test out in the parking lot. There's a requirement during this test that the septum, which is the highest point of these radiating lines, needs to be 3 times the height of the EUT. And in this case, we were testing like a 6 or 7 foot high EUT, so the height of the lines had to be somewhere around 20 feet high. If it's possible to have to accomplish the height within a test chamber, and then also to meet an additional clearance off of the top of the lines, between the top of the lines and the absorbers of the test chamber, which is usually you can find guidance from the generator manufacturer for that, and it is allowed to do this test inside of an EMC chamber. However, it's usually limited in EUT size that can be tested there. This was a fun and challenging test. We had to build a large ground plane, which is like 50 by 100 feet, out of mesh wire. We had to attach all these rolls of mesh wire together in a conductive fashion underneath the setup. So it was quite an extensive setup for that test. Also, when we did this test, we followed clearance guidance from the generator manufacturer from the building and other electronics like cars and other equipment in our facility. However, the I guess overshoot of the pulse did still manage to damage a building alarm panel and scramble a test chamber control panel in a nearby building. So the next couple slides I'll highlight what are considered, I guess, the biggest changes, significant changes to version G, and some other miscellaneous changes. So one of the big changes in version G was that a test method was removed, CS106. So CS106 is a conducted susceptibility pulse test. It's kind of like a double exponential waveform pulse. And it was actually developed and added just in the previous version, F. And in version F, they explained that CS106 was based on an older test method from the early versions of MIL-STD-461 versions A through C, where they just had a 4-digit test designator name, and it was called CS06 there. So CS106 was just a slightly modified version of CS06, but in version G they decided to remove it again, so it was only in version F. And version G provided the rationale that it was concluded by the standard committee that CS115 and 116 already meets the intent behind the reintroduction of CS106. So there is a longer explanation than that in the appendix of the standard. If anyone's interested, you can go read through that. They explain how they came to that conclusion. Another significant change was the addition of CS117, which is the lightning-induced transient susceptibility test. So this is a new test method. There was never a number CS117 prior to version G. And CS117 is performed to simulate the indirect effects of lightning striking platforms. So if lightning strikes an aircraft carrier or a plane or any type of military vehicle, it's going to induce disturbances onto the wiring harnesses and onto the chassis of that platform. And then all the electronic equipment that's operating in that platform, all the electronic equipment is going to experience to some extent the disturbances and the transients that are a result of that lightning strike. So,
how's it going, guys?
So this is a new test method and to MIL-STD-461G. However, it's not a brand new test method in the industry. This test method was taken from and modified from RTCA D0160, section 22. And that test has been around for quite some time, that test method. Within MIL-STD-461G, the applicability is explained, and you could summarize as saying that the applicability is mostly to safety critical equipment and equipment and cables that are connected to safety critical equipment. There are some other pieces of equipment that are listed as applicable as well. And this test method includes waveforms 1, 2, 3, 4, 5A, and then waveform 6 from RTCA D0160. There is also a waveform 5B defined in RTCA D0160, and that one's not carried over at all into 461G. This test includes different levels for internal and externally mounted equipment. So if equipment is mounted external to the platform, then the test levels are more severe. The application of the test in the lab is done with a clamp. It's an inductive coupling where a clamp is placed around the cable bundle. RTCA D0160 also included an additional application method where you directly inject to pins, and that is not carried over into 461G. So the next slide just shows a few of the setup diagrams from the standard. You can see that for the calibration setup, the transient generator feeds into the injection transformer, and then a calibration loop is placed through that injection transformer for monitoring current with an oscilloscope, and then also a voltage probe is connected to the oscilloscope to take the voltage measurement on the output of the injection transformer. And then for the test setup, the calibration loops are removed, and a current monitoring probe is used and the voltage probe is still used during the test in order to measure the amplitude of the disturbance, current voltage and current portion of the disturbance that are coupled into the EUT, the equipment under test. And so the next significant change to 461G is the addition of CS118. And again, CS118 method number that it didn't exist before version G, so they created the new number and added ESD, electrostatic discharge testing, to 461. Prior to version G, many projects that we saw at MetLab did include ESD testing. They would just, the contract would reference a separate standard for that. And at this point, the committee for MIL Standard 461 decided it was appropriate to include ESD as a test method within MIL Standard 461. So it's not new, it's not brand new in the sense that most equipment had been tested for ESD prior. It's just they were doing that under separate standards. So this photograph just shows a close-up of the tip of the electrostatic discharge generator actually arcing, the output discharge is arcing to a piece of copper on the chamber. And it's just a picture to demonstrate that this is a high voltage test. So I'll go into the test levels called out in MIL Standard 461, but the test levels of the generator, most of the ESD generators can generate up to 30,000 volts, and when you start to get into the tens of thousands of volts, you can actually visibly, easily see the arcing that takes place. So CS118, they call it personnel-borne ESD discharge. That means that when we're doing this test, we're simulating the same type of discharge that you might have, everyone might have experienced on a cold, dry day. You go to open your car, you get a shock from your metal chassis of your car. That's an electrostatic discharge because your body has a different potential compared to the chassis of the car. So you discharge your stored electrical charge to the chassis of the car, or the car to you. And it stings a little, but most people don't realize that discharge usually is in the range of 2,000 to like 15,000 volts. It's just it's a very low current and a very short duration, so it's not damaging or lethal in any way. But it is a very high voltage, and it can be very damaging to electronic components, digital components. So this new test method is based on IEC 61004-2, which is an old and maintained ESD standard that has a very well-defined procedure for the test. And it's applicable to equipment that has any man-machine interface. So any equipment that normally a human would have to touch in order to operate that electronic equipment, then their body could discharge to that electronic equipment. And so the standard requires contact discharges up to plus and minus 8,000 volts, and wherever contact discharges can't be applied, air discharges up to plus and minus 15,000 volts. So the way that the contact discharges work is there's a sharp tip on the generator that is actually placed in contact with conductive surfaces, so metal surfaces, or could even be a composite or carbon surfaces of electronic equipment. And then the generator is discharged to transfer the pulse to the chassis or to that surface of the equipment under test. Air discharges are used where the surface of the equipment under test is covered with a non-conductive material like a plastic. And that test is done to test for the possibility of arcing through that non-conductive material to a conductive surface that is behind that non-conductive material. So for this presentation that I'm using my laptop computer, the majority of the surface of the laptop computer is plastic. So if I was going to perform an electrostatic discharge test on this laptop computer, I would mostly be using air discharges to see if the tip would discharge through the small openings around each key on the keyboard and on the mouse pad and things like that. Whereas if you're testing an electronic chassis that's going to be mounted in the deck of a ship or something, it might be all metal, so you would mainly be using all contact discharges with the sharp tip right to the metal chassis of that device. And for every test in MIL-STD 461, there's some type of, they either call it a system integrity check or a verification or calibration. All those checks, and ESD has it as well, are some kind of check to make sure the test equipment is working accurately and properly right before each time that the test method is performed. So for CS118 ESD, there's a special electrostatic voltmeter that's used to measure the voltage of the test generator, and then there's a target, they call it, which is a small metal disc that has an array of resistors around it that connect it to a Faraday cage. So when you discharge to the center of the target, and that target has also a coaxial output on it that gets connected to an oscilloscope, you get a controlled measurement of the current that's generated. You can measure that current waveform as well as the rise time and other parameters with a oscilloscope. So that's those are what I would consider the most significant changes that the test method changes. And now I'm going to go through some other miscellaneous changes that were made for various existing test methods and also some of the general sections of the standard. So one of the changes that was made is that now when in version G, when a floor standing EUT, something that's designed to be mounted on the deck or the floor, is tested, now they've added the requirement to use a table next to the equipment under test. Prior versions, you would route the cables from the EUT down to the floor, down to the ground plane on the floor. But now in version G, they require that ground plane to be raised up on a table, just like if you're testing a tabletop device. So there's also some changes made to the CE 102 test. One of the changes is that there's an additional LISN verification. So in addition to the test system calibration, there's now another check that's done, which is impedance verification of the LISN. And they have you send a 90 dB microvolt signal into the LISN and measure that with an oscilloscope. Then they have you measure that 90 dB microvolt signal directly without the LISN, and you take the ratio of the measurements, and the ratio of those measurements has to fall within the requirements given in the standard, which is at 10.5 kilohertz, it has to be minus 14 dB, and at 100 kilohertz, the ratio has to be minus 3 dB. Some of the other change, another change that was made is to CS114. So for CS114, the new thing in version G is that there's now 2 of these calibration fixtures used. So one of the fixtures is used to put the monitoring probe around, and during the verification, you actually just put a coaxial load on that probe. But then during the test, you're going to actually have the monitoring probe connected to a measurement equipment. So that's new. And then another change to CS114 is that when you're doing the verification, they allow you to run the scans with a minimal dwell time and twice the normal step size. So that allows the verification portion to be completed faster. The reason that is okay, and the rationale I'm sure that the committee had that makes that allowed, which I've seen in other conducted emission standards, is that the equipment operates fairly linearly. So if you just minimize the frequency points, you can linearly interpolate other values between data points, and you can expect that they're going to be the same as if you'd taken additional measurement frequencies. RE102 applicability changed, where they no longer have you determine the upper frequency range of measurement based on the highest intentionally generated frequency within the EUT. They just require now that all tests are performed up to 18 gigahertz. Prior versions of MIL Standard 461 allowed you to limit the upper frequency range of tests if the EUT didn't have any sources of very high frequency within. Another change that was made to RE102 is that for freestanding EUT, the antenna height shall be determined as described in these subsections, and they changed the wording to use the word width. I'm sorry, to use the word area instead of width when determining how many antenna positions you need to do based on the beam width of the antenna. So now, since they use the word area, you have to consider not only the width of the EUT, but the height of the EUT. So in the previous versions, you may have tested 3 antenna positions from left to right on the floor in order to cover the full width of an EUT. Well, now you may end up doing 6 or 9 if the EUT is also a tall EUT in order to cover the height of the EUT. And for RS-103, the same change was made in the wording with using the word area so that you account for the height of the EUT when considering the beam width of the test antennas and determining the number of additional test positions that an EUT needs to be tested at. So this all translates to longer test time in some cases. So that's an overview of the main changes. There are many other small wording changes that were made, and mostly for clarity, in order to, from what I can see, in order to clarify statements to make those more easy to interpret. And I do have a full list of changes that we can somehow make available if anybody's interested. You can contact us. It's just a literally like line-by-line comparison of the standards that has all the small wording changes. So I just wanted to quickly go through some of MET's related capabilities. We have just to make sure it's clear, the full testing capabilities for MIL Standard 461, meaning we can conduct all the methods to all the versions, including all the highest test levels, and we can fully test the version G. We've already been equipped to handle the new test methods that were added to 461 because we were already doing those test methods for other standards. And in addition, we can also perform testing to RTCA DO-160. That's the testing for commercial aircraft equipment. A lot of manufacturers that we test for make both military and commercial aircraft equipment. We can handle both of those categories. We also perform quite a bit of testing for shielding effectiveness, most often to the standard IEEE 299. We can perform that testing on enclosures anywhere from small to large, and we can also use that method to perform testing on small sheets of material by mounting those sheets of material in our shielded chamber and then measuring the shielding effectiveness of our shielded chamber with the different material mounted in the window opening. And that test has proved very useful for clients who are making materials such as composite materials to make UAV chassis or composite materials for other applications. And we've had some clients that test many different variations of their chemistry in those materials, and it helps them determine the most effective chemistry to help with their design of composite materials. We also do quite a bit of testing to military power quality standards, which is MIL Standard 704, 1275, and also 1399-300. Those are 3 standards, one for each platform, ships, military vehicles. I'm sorry, aircraft is 704, and then 1275 is ground vehicles, 1399-300 is ships. And those standards they include voltage variation, frequency variation, power transients, and things that would be encountered when you connect equipment to the power systems on those platforms, and it ensures that that equipment is going to work properly on those platforms, and it's not going to cause interference to other equipment powered on those platforms. So we have the capability to perform all that testing. And then some of the unique capabilities that we have are, we have a 45,000 kVA, a 45 kVA programmable power supply. We also have the RF filters that handle that power into our chamber, which is a kind of a unique capability. And we do have multiple chambers side by side, so we can handle several projects at a time, or for other projects we've tested multiple units at simultaneously using more than one chamber. We have a reverb chamber, and that can generate up to 20,000 or over 20,000 volts per meter radiated susceptibility pulse levels. And for the DO-160 section 22, which is now also the CS-117, we test all the waveforms and all the test levels. And as I had shown in the photo, we can do the RS-105 HEMP testing, high altitude electromagnetic pulse testing up to greater than 50,000 volts per meter. So that was the presentation, and if there's any questions, I'd be happy to read those and try to answer those now.
If you have any additional unanswered questions, please contact us via phone or email. We will follow up with an email that will include a link to the presentation. It will also be on the website. But that concludes our webinar. Thank you for joining us today.